Bismillahirrahmanirrahim. Now we have our next topic is how we can compute the Fourier coefficients and the value of the piecewise function from the diagram. So I start with an example here. Example f of x is equal to 1. The value of the function is 1 and 2. And as we know, it is a piecewise function, so the value of the function is in the interval from 0 to pi, and the value of the function is 2 in the interval from pi to 2 pi. Before this, we are discussing about the periodic interval, and the function is defined. Here it takes half of the interval. As we define that its value starts from minus p to p, or from minus pi to pi, minus 2 pi to plus 2 pi, minus pi by 2 to plus pi by 2. But at this time it defines the function from 0 to one end, from 0 to the positive end. So it divides the interval, it halves the interval. So in this case, we just take the value of the interval or the limit of the integral from 0 to 2 pi. Other things remaining same. So we start the question. Given interval is from minus p to p, and its value is from, as you see here, from 0 to 2 pi. So 0 to 2 pi, if you calculate the total length of the interval, what you have to do, you have to subtract the first one from the second. When you do this, p minus p, it becomes 2p is equal to 2 pi minus 0 is equal to 2 pi. So p is equal to pi. Okay. How you can see, I'm stating here, you just do this. P minus p is equal to 2 pi minus 0. In this way, minus plus, so p plus p is equal to 2p is equal to 2 pi. So 2p is equal to 2 pi, which implies p is equal to pi. Now before this, I am telling you the Fourier coefficient, the value of the Fourier coefficients, in which the first coefficient is a0, and you know what is its value. Its value is 1 over 2 pi from range from 0 to 2 pi. Before this, I am telling you the interval of the integral varies from 0 to the 2 pi. So 0 to 2 pi f of x dx, what is the value of p? That is pi. So you substitute here the value of p, that is equal to 1 over 2 pi from 0 to pi. And you know that interval is a piecewise interval, and its value varies from different sections. From 0 to pi, the value of the function is 1. From pi to 2 pi, the value of the function is 2. Here we have a complete interval 0 to 2 pi. As you know, here there is no value that lies from 0 to 2 pi, but from 0 to pi there is a value, and from pi to 2 pi there is a value. So we split this integral into two parts. First we move from 0 to pi according to the given interval. First we move from 0 to pi, and you substitute the value of the function here. What is the value of the function in this interval is 1, plus from pi to 2 pi, in this interval the value of the function is 2. So I substitute here their respective values. Now I am integrating it. This is 1 over 2 pi, and the integral of, the integral of 1 is x from 0 to pi, and the integral of 2 is 2x from pi to 2 pi. Now you substitute there, you evaluate this integral to its limits. It become upper limit minus lower limit, pi minus 0 plus 2 into upper limit minus lower limit, 2 pi minus pi. So it is equal to 1 over 2 pi into 2 pi plus 2 pi minus pi, 2 pi. So you get here 2 pi plus pi, that is equal to 3 pi divided by 2 pi. It is equal to 3 pi divided by 2 pi. Pi is cancelled with this pi. You get it is equal to 3 over 2. So in this way you get the coefficient of the first coefficient of the Fourier series is equal to 3 by 2. Now we move towards second coefficient of the Fourier series, that is an, and its value is 1 over p, and its the interval of the integral is from 0 to 2 pi f of x cos n pi x over p. And you know what is the value of p? That is pi. Now you substitute here their respective values of the p. So when you substitute this, 1 over pi from 0 to 2 pi f of x cos n pi x over pi dx. As you see here, this pi is cancelled with this pi, and after simplification you get from 0 to 2 pi f of x cos nx. Now this integral is a piecewise integral, so you again split the function. When you split the function, it moves from 0 to pi cos, and in this interval the value of the function is 1. You substitute here 1 cos nx dx, and the other integral is pi to 2 pi, and in this interval the value of the function is 2 into cos nx dx. And when you see that integral of cos nx is equal to sin nx divided by n. When you integrate this, its integral is sin nx divided by n, and its integral is sin nx divided by n. As you see here, the value of the limits are, that is pi and 0. When you evaluate sine at this pi, and you know that sine, the value of the sine at pi is equal to 0, and when you substitute 0, sine is again gives answer 0. So I am writing clearly here, the value of the sine in this interval is 0. There is no need to evaluate the function if you see such type of limits where the function gives its answer 0. So you directly write there 0 in this way. Again you check here. Here you see n is a number which varies from 1, 2, 3, 4, 5. When you substitute here this limit n pi, when you substitute the value of n, it becomes sine 1 pi, sine 2 pi, sine 3 pi. The value of the sine at pi is equal to 0. The same case is here. So in this way you get its answer is 0. Now we move the third coefficient of the Fourier series, that is bn is equal to 1 over p 0 to 2 pi f of x sin n pi x over p dx. Again you substitute the value of p. You see here p is equal to pi. You substitute here the value of p here, 1 over pi 0 to 2 pi f of x. When I substitute the value of p here, pi, this pi is cancelled with this pi, and after simplification I write here sin nx. Now split the integral over the limits 0 to pi. In this interval the value of the function is 1 sin nx dx plus from pi to 2 pi. Here the value of the function is in this interval, that is 2, and then sin nx dx. When you integrate this, you get 1 over pi minus cos nx over n 0 to pi plus 2 minus cos nx over n from pi to 2 pi. This portion goes wrong, so I write in a block. Now 1 over pi minus 1, I take this minus 1 over n as a common outside and check the function at the given limits, cos n pi minus cos 0, minus 2 over n similarly, and check the function, check the integral at the given values, and it is cos 2 n pi minus cos n pi. Cos n pi, and you know cos 0 is equal to 1 minus 2 over n cos 2 here when you substitute the value of n here. And other important thing you note here, you in your intermediate classes you know a theorem, that is De Moivre's theorem. De Moivre's theorem. What is its definition? If some power come, if a function has some power, then it is right as a multiple of the angle, as a multiple of the angle. In the same way, we are writing here, as you see here, cos 2 n pi. I am writing here cos 2 n pi as cos 2 pi whole raised to the power n, in the same way. And you know that cos 2 pi is equal to 1, and 1 raised to the power n, it is equal to 1. So I'm using this theorem, De Moivre's theorem, and use its application at this place. 1 over pi minus 1 over n cos n pi minus 0 minus 2 over n cos 2 n pi minus cos n pi. Cos n pi, at this point I am not simplifying this, just evaluate their values at 0. So cos 0 is equal to 1 and cos 2 n pi is equal to 1 minus cos n pi. Open the brackets, minus cos n pi over n plus 1 over n minus 2 over n plus 2 cos n pi over n. Take n as an LCM, so then it becomes minus cos n pi plus 1 minus 2 plus 2 cos n pi. As you see here, 2 cos n pi minus cos n pi, you get 1 cos n pi. That we get 1 cos n pi minus 2 plus 1, that is equal to minus 1. So 1 over pi into cos n pi minus 1 over n. Now I use here the concept of De Moivre's theorem here. As you see, I am taking this multiple n as a power of the function cos pi raised to the power n minus 1, and you know that cos pi is equal to minus 1, so minus 1 raised to the power n minus 1 divided by n pi. So required Fourier series is in this way. You get f of x is equal to a naught plus summation n is equal to 1 to infinity a n cos n pi x over p plus b n sin n pi x over p. This is our Fourier general form of the Fourier series. Now you substitute their respective values of the Fourier coefficients. What is the value of the Fourier coefficient? As you see here, a naught is equal to 3 by 2. So you substitute here the value of a naught, that is 3 by 2 plus summation runs from 1 to infinity. And you know what is the value of an is equal to 0. You substitute, when you substitute an is equal to 0, this total term becomes 0. I write here 0. Plus, and you know what is the value of bn. Recently you find that is minus 1 raised to the power n minus 1 over n pi. You write here minus 1 raised to the power n minus 1 over n pi, and you write here sin n pi x over p. When you substitute here the value of p, that is pi is cancelled with this pi, and remaining terms are sin n x. So in this way you find a Fourier series. Okay, I think this all thing you understand very well. Now we move towards its exercise. Exercise is 11.11, question number 1. Here f of x is equal to 1. Here f of x is equal to 1. Before going to this exercise question, I want to describe the graph of the previous example. If we see here, the graph of, and this is a function 1 over 2, the interval is from 0 to pi and pi to 2 pi. You draw a plane here, one named x and the other named y, and draw the point 0 to pi, then pi to 2 pi, and on the y-axis you have the function's value 1 and 2. You draw here, that is 1 and that is 2. Clearly it is from 0 to pi, the interval, the value of the function in this interval is 1. So you write parallel to 1 in the interval from 0 to pi, you draw a line. You draw a line here. Then when you move from pi to 2 pi, the value of the function is, in this interval, the value of the function is 2. So you see here, the value of the function moves from pi to 2 pi along 2. So there is a discontinuity. There is a discontinuity, which I am telling you in the, I was telling you in the previous lecture that it behaves very good in the discontinuous functions, in the case of discontinuities. So this is its graph, and you can draw their graph in this way. And other techniques that they comes in our question, I am also telling you with the with each case. Now we move towards question, that is question number exercise 11.11. The first question is f of x is equal to 1, that is its interval is from 0 to 2 pi. Find the Fourier series and also draw its graph. I'm not writing here the graph, I'm not mentioning here the graph. Just first you find the Fourier series, then I will explain you how you can draw its graph. And you see, you find the value of p, the interval is minus p to p, and the given interval is from 0 to 2 pi. So the total length of the interval here is 2 pi, and the length over right side is 2 pi. 2 is cancelled with this 2, you get the value of p is equal to pi. As you know, a naught is equal to 1 over 2p from 0 to 2 pi f of x dx. You substitute here, now the function value contain only one function value. You substitute here the value of the function, that is 1, and when you integrate this, and you get a naught is equal to 1. And the other way, the second Fourier coefficient is an, 1 over p from 0 to 2 pi f of x cos n pi x over p dx. You substitute here the value of p, that is pi, as you see here. You substitute here the value of p, that is pi, from 0 to 2 pi f of x cos n pi x over p. I am substituting here the value of pi here, p here, as you see here, 1 over pi 0 to 2 pi, and I substitute the value of the function, that is 1 cos n pi x over pi. Pi is cancelled with this pi. After simplification you get 1 over pi 0 to 2 pi cos n pi, nx dx. When you integrate this, you get sine n x over n from 0 to 2 pi. And as you know there, the value of sine at 2 pi gets 0, and when you check the value of the sine at 0, it is also 0. So I am crossing here and write it 0. In this way, the coefficient of an is equal to 0. Now we move another coefficient of the Fourier series, that is bn is equal to 1 over p from 0 to 2 pi f of x sine n pi x over p dx. Its value is 1 over pi 0 to 2 pi, and substitute here this respective value of the function, that is 1, and sine n pi x over pi. Pi is cancelled with this pi. After simplification you get 1 over pi from 0 to 2 pi sine nx dx. Is it clear? Now 1 over pi, when you integrate that, that is equal to minus cos n pi over n from 0 to 2 pi, minus 1 over n pi cos, substitute there respective limits, cos 2n pi minus cos 0. I'm using the De Moivre's theorem here, minus 1 over n pi, I'm take n this outside, it becomes minus 1 over n, and using here the De Moivre's theorem, it is equal to cos 2 pi whole raised to the power n, and cos 0, you know what is its value, that is 1. So you know cos 2 pi is equal to 1. Cos 2 pi is equal to 1. 1 raised to the power n minus 1. So 1 takes any number, 1, 2, 3, 4, 5. Its value is 1. So you see here, after simplification you get 1 raised to the power n is equal to 1. 1 minus 1, it is equal to 0. So our required Fourier series is f of x is equal to a naught plus summation n is equal to 1 to infinity an cos n pi x over p plus bn sin n pi x over p. As you see here, the value of the Fourier first coefficient, that is a naught, and its value is 1. And at the other, the values of the other Fourier coefficients are a naught, as you see here, its value is 0, and the value of the bn is also equal to 0. When you substitute their respective values at the place of a naught, its value is 1, and the other coefficients are both an and bn are 0. This total expression gets 0 value. So when we look at, there is no fluctuation. The Fourier series coefficients define the fluctuation in the graph. The trough and the crust that produce in the graph, as you see in the sinusoidal waves, how graphs goes up and how graph comes down, up to which value. This shows the intensity level of the from these coefficients you understand the intensity of the graph of the function. So when we look at the graph of the function, here graph of f of x is equal to 1 over 0 to 0 is less than or equal to pi, 0 is less than or equal to x, or x is less than or equal to 2 pi. So in this way, in the total interval from 0 to 2 pi, the value of the function remains 1. So we say that it is a graph of the constant function. It is a graph of the constant function. So f of x, as you know that we say y is equal to f of x. F of x represent the value of the y. So you draw a point, mark a point, and give its value name 1, and draw the interval from 0 to pi, and then pi to 2 pi, and this intervals, in the whole interval, the value of the function remain same. So you draw from start the line from 0 and up to 2 pi, it remains same, that is 1. Okay, so in this way our this lecture comes to end. Inshallah Ta'ala, we will meet with the question number 2, and I am explaining you how you can solve this question over the different intervals and find the Fourier coefficients after solving the Fourier series. We will meet in the second video with question number 2. Take care. Allah Hafiz.